Graph theory. When we talk about graph theory, we talk about nodes, vertices, edges, simple graphs, cycle, pseudographs, complete graphs, bipartite, biconnection, branch width, canonization of formic equivalence, Freud's theorem, Adwire conjecture, amalgamation, disperser, expand graph, graph, cycle graph, and all of that complicated graph theory terms that can make up an entire alphabet. What we normally don't think about when we hear graph theory is sex. In fact, we are gonna use graph theory to address a decades-long debate concerning the relative promiscuity of men versus women. Now, graphs come in all sorts of applications: scheduling, optimization, the design and analysis of algorithms. In fact, several graduate students became millionaires because they use graph theory in a clever way. But, let's talk about sex. The issue that we are gonna address today is one of the most talked about and most well-studied questions in all human sociology. On average, who has more opposite gender partners, men or women? Now, pause this video and take your time to decide. Do you think men on average have more opposite gender partners than women do? Or do women have more opposite gender partners? I've asked people about this several times, and typically they say that men in general have more opposite partners. Some responded that women have more partners, some say it's equal, while for a few, well, there's just no way to know. It's hopeless to figure it out. Alright, well, in the popular literature, pretty much universally, it's believed that men have more opposite gender partners than women. In fact, when you think about this question, you always think of men leading hearts and men having multiple wives, not the reverse. Now, not surprisingly, this issue has been studied scientifically extensively in one of the largest studies ever done. Researchers from University of Chicago interviewed 2,500 people at random over several years to try to get the answer once and for all. And they wrote a 700-page book called The Soul of Social Organization of Sexuality, Sexual Practices in U.S. This study concludes that on average, men have 74% more opposite gender partners than women. When you think about it, that sounds reasonable. That might be okay. But not according to ABC News. They did a poll of 1,500 people in the country in 2004 and concluded that the gap is much greater. In particular, in the study, they said that the average man has 20 partners and the average woman has 6. And this gives it a percentage of 233%. Okay, now who do you think is right? 74%, 233%. University of Chicago ABC News. So how do you tackle this problem? Maybe we can do our own research survey. I don't know how much we'd really learn and how many decades long it would take. So I don't think we can do that. But fortunately, this is the kind of question that can be answered by graph theory. Graph is just a bunch of dots and lines. The dots are called the vertices, also referred as nodes. Get two vertices, connect them, and you form an edge. Get another vertex, connect them. Now you have a graph. We can label these vertices and edges. This vertex is called E, this one is B, then C, and D. The edges are AC, BC, and CD. Next is the degree. Degree is defined to be the number of edges connected on one vertex. For example, vertex A has 2 edges connected to it. Thus it has a degree of 2 while vertex D only has 1 edge, giving it a degree of 1. Now, let's differentiate a path in a circuit. A path is a sequence of edges that connects all the vertices, and does not go through a vertex more than once. On the other circuit is a path that ends where it begins, at the starting vertex. Adjacent vertices to a given vertex can be counted by knowing if the given vertex is connected by an edge to another vertex. In this figure, E's adjacent vertices are B and C, while B's adjacent vertices are A and C, and D only adjacent to C. Pendant vertex is a vertex that is very loyal. Why? Because pendant vertex has only one edge, connecting it to only one vertex. Of the given example, D is the only pendant vertex, while all other vertices have polygamous relationship, sadly for D. Okay, enough with the polygamy. Let's go with as neighborhood. Neighborhood simply refers to all of the adjacent vertices to a given vertex. Well, take all the edges as the streets and the vertices as the corner. If A is a corner and C is the other corner, the street along it is the neighborhood, so A and C are neighbors. So as with A to B, and B to C, D's only neighbor is C as A and B are too far from this corner. Now, let's say there is another vertex C not connected to any other vertices. He's introverted and doesn't want to have any connection with other vertices, so he chose to be alone. This vertex would then be called as the isolated vertex, a vertex that has no connected vertex. So, we're done with the parts and simple concepts about graph. But what about its types? Let's talk about it. First is null graph. From the word itself, null, which means zero, is a graph with zero edges, or zero connected vertices. Just a bunch of loner dots. Second is the simple graph. It is simply a graph that has edges connecting two different pairs of vertices. No loops or multiple edges connecting two vertices more than once. Simple, isn't it? For the third and fourth is the multigraph and the pseudograph. A multigraph is a graph with multiple edges on at least two same pairs of nodes, while a pseudograph also has the property that allows multiple edges on two same pairs of vertices, but with the addition of being allowed to have loops on a vertex. To visualize it, let your house be vertex A and your neighbor's vertex B. You decided to go to your neighbor's house to play with friends. But when you get there, you forgot something in your home, so you get back to your house. This is now an example of multigraph. Now you're going to your neighbor's house again. But only a few feet away from your house, you remembered that you forgot to lock the doors and decided to get back immediately. This is now a pseudograph as you loop to your house without going through other houses. Let's go to the fifth and sixth type, the undirected graph and directed graph. Technically, an undirected graph is a graph where edges have no specific directions. A and B is connected but not specific whether A is to B or B is to A. While directed graphs are graphs with directed edges or arcs, A is connected to B or A is connected from B. Next are the connected and disconnected graphs. A graph is connected if all pairs of vertices are connected. This means that every two vertices are connected by an edge or a path. Otherwise it is a disconnected graph, as at least two vertices are not connected by an edge or path. Lastly, is the regular graph. A graph that has the same number of degrees of vertices. A graph that promotes equality among its vertices, while a principal graph. So that's it for the types of graphs. Oh wait, I almost forgot. We still have the special graphs. A graph that has extra toppings. Well, let's see. Complete graph. A graph where every two pair of vertices are connected only by one edge and all vertices are connected. What a well-socialized graph. Next is a cycle. A graph consisting of a single cycle where all edges loops over its vertices. Coming alongside the cycle is the wheel. It is just like a cycle, but with a vertex in the middle connecting to all other vertices, like a wheel in a colessa. Another special graph is the bipartite graph. A graph where vertices can be partitioned into two set, bi or two, partite, partition, in which one set of vertices is connected to one or more vertices of the other set, but not connected to vertices of the same set. A complete bipartite graph is a variant of bipartite graphs, where all vertices in one set are connected to all other vertices of the other set.
Now that we've defined what a graph is, how do we use a graph to model the issue with opposite gender partners? Simple. We represent the nodes of the graph as the people. There's two kinds of people here. Men and women. We have nodes for the men and nodes for the women. We can name these nodes. This node is Tom, this is Ben, Jude, Keith, blah blah blah. Then on the women's side is Nicole, Penelope, Kitty, and more. The edges represent partners. Tom and Nicole are partners, so connect them. So is Tom and Penelope. Then Kitty, and more. As you can see, this is an example of a bipartite graph. In the USA, the number of opposite gender partners, or the number of nodes, is about 300 million. The number of men nodes is 147.6 million. Women have about 152.4 million. What about the edges? We don't know. The surveys can't estimate it. What we are trying to figure out is the ratio of the average number of opposite gender partners in men to the average number of partners in women. This represents the average degree of the men to the average degree of the women. What is AM over AW? Chicago says it's 1.74 because it's 74%. ABC News says it's 3.33 because it's 233%. AM over AW is equal to 1.74 or 3.33. Now, let's see if this is true. What is AM? The opposite gender partners for men is the total number of partners they had divided by the number of men. It's the number of edges divided by the number of nodes. Same goes for the average in women. Now, divide both of these equations together and you can see that we can cancel the number of edges out. Thus, the ratio of the average number of opposite gender partners in men to women is just the number of women divided by the number of men. The number of men nodes is 147.6 million. Women have about 152.4 million. Divide those, and the result is about 1.0325. Now we just proved that a man has 3% more partners than women. No need to do the interviews or spend years doing. We just spent 5 minutes solving what took a decade-long research with graph theory. This is the answer. University of Chicago is off, ABC News is way off. This has nothing to do with the promiscuity of men or women. It takes two to tango. For every guy, you have one woman. If there's more men, then there's more partners for women. If there's more women, then there's more partners for men. Simple. In fact, there are more bogus studies like this, and graph theory helps disprove such myths. Graphs usage is not limited to only these areas. Graphs are applied differently in the fields of mathematics, chemistry, social science, engineering, and computer science. But for now, let's focus on its application in computer science, specifically network topology. Okay, so let's define first the network topology. In computer science, this refers to the physical and the logical arrangement of connected devices. It can also describe how data can be transferred from device to another within the network. In this matter, the devices such as routers, computers, and/or servers are considered as the nodes, while their physical connections through wires and/or cables are the edges. We'll discuss the bus, star, ring, mesh, tree, and hybrid topologies and their pros and cons, so sit back and relax, and have your snacks with you as you listen. Bus topology refers to a network connection where all devices are connected to one single line known as bus. Data are transferred through this line to its destination device. Bus topology is suitable for small network connections. It is inexpensive and easy to set up. However, bus topology is not advisable for networks with higher traffic, and it is harder to identify problems in this setup. Moreover, the single-line cable is a very crucial part of this, as when it is damaged, the entire network won't go well, so protect that single line to keep this network going. Next is the star topology. It is a network topology where all devices are connected to one central hub. It can be a router, switch, or server. This central hub controls the data transfer of the devices connected to it. This setup proves less a security hazard, easier problem identification, and allows addition and removal of other devices from the central hub without affecting the entire network. But the number of connected devices is limited depending on the capacity of the central hub. It is also expensive, and when a problem occurs on the central hub, the entire network will be affected. What a hassle it would be to fix it. On the other hand, the connection of devices in ring topology is sequential, where device 1 is connected to device 2, and device 2 connected to device 3, and until it reaches the last device in the network, where the last device connects to the first device, forming a loop-like structure. This will provide a unidirectional flow of data, as data would traverse every devices between the source device to the target device. Plus, it will be easy to distinguish network problems in this setup. Some disadvantages of this, however, is when a problem occurs to one device, data will not be able to transfer through it, affecting the entire network. Data transfer also slows down as it traverses through more devices, and when changes are made in one device, changes might also be needed in other devices. Having one direction leaves you with only one choice. Another is the mesh topology. Every node is connected to every other node, making it connected to each other devices, thus allowing data transfer through various connections. This is suitable for high-traffic networks, as it allows data to be transferred faster. A problem in one device will not result in network failure, as data can be transferred in all its connections. Although, this connection is highly expensive, and it requires large numbers of cables, and is too complex to set up. Think well or things might become meshy. Second to the last is the tree topology. It comprises a main or root node connected to sub-level nodes, which are also connected to more sub-level nodes. That's why it is called tree. It can branch out and make way for nodes to have connections. Physically, this is like a combination of bus and star topology, where the foremost level nodes are connected to one central node, and these central nodes are connected in a single bus that is connected to one main node. This is advantageous for networks that require a series of star topologies to be used independently, plus it's versatile and expandable, and failure on one node will not affect other node connections, and will only affect sub-level nodes connected to this node. Given the convenience of having star topology, it also has downfalls. It is hard to maintain as it has large connections, highly expensive, and when a problem occurs in the main backbone or root node, the entire network will fall. Just like a tree losing its roots, unable to sustain and grow. Lastly, the hybrid topology. It is a combination of any network topologies aforementioned. A resulting network topology where at least two network topologies are combined in making connections. Using hybrid topology allows flexible arrangement of devices. Any possible combination of network topologies can be done to achieve a desired setup. This is suitable for vast networks, as it will allow different ways to secure connectivity between devices, and is very effective for the users and data transfers. This advantages comes with disadvantages too, as its complexity is greater and installation is more complicated. This is also way too expensive, especially when combining expensive setup. Well, a hybrid difficulty for a hybrid device connection. As you can see, graph theory is widely used to help improve our lives. From guiding us to the truth and proving conspiracies wrong, to optimizing communications within networks. Graph theory is used everywhere, whether you know it or not.